Hello, hello, and welcome to your first lesson in AP Calculus AB. You might notice that this video says Day 2. Day 1 for my classes are always the syllabus and procedures, a little bit of review, but this is really our first day of actual calculus. Now, calculus, at least in Calculus AB, is split across 3 topics. The first topic is all about limits, and that's what we're going to begin with today. The title of our topic is Limits and Continuity. Limits really provides the foundation for the other 2 topics of calculus, and we actually spend the least amount of time on limits. They're a pretty easy concept to get down, but it's the expansion of limits into our other 2 topics, derivatives and integrals, that we're going to spend the majority of our time on. In fact, the entirety of the rest of this first semester will be spent on derivatives, and second semester up until the AP exam on integrals. But for now, for the first 10 or so days, we're going to learn all about limits. These lessons are set up so that there are some daily learning objectives. They're telling you by the end of this lesson you should know a couple things. Here you should be able to tabularly interpret and estimate two-sided limits. We'll talk about some of those words later on, and express tabular limits symbolically using correct notation. So at the end of the lesson, you should ask yourself, do I know how to do those 2 things? And if you don't, check in with me or your teacher, whoever that might be, to make sure that you actually understood what you were supposed to for the lesson. Also, the title of the YouTube video, or at least the day of the YouTube video, might change here and there. So for example, this YouTube video might eventually be titled Day 3, but this lesson still says Day 2, and that's because from year to year I shift certain lessons around, but I don't want to re-record all 120 or so of my videos. That would take forever, so I just retitle them. I'm actually redoing my entire limits section this year. This is 2022. You can see our calendar down here. Because I didn't really like how it went the last couple of years, and I think I can do a better job, so hopefully I'm right. Let's go ahead and get started. For today, you are definitely going to need a graphing calculator. In fact, you should have a graphing calculator available for every lesson. We might not always use it, but I do my best to incorporate a graphing calculator at least once a lesson. Remember, our AP exam, and if you didn't know, now's the time to learn, our AP exam has approximately a third of the problems where you have to use a calculator. It's not one of those where it's like, oh, I can figure it out without. No, you cannot do the problem without having a graphing calculator. We're going to talk more about the 4 ways you're expected to use your graphing calculator as you move on through, and in fact, we're going to see one of those uses right now. So to start off our lesson for today, I would like you please to quickly graph y equals x plus 2 and y equals x squared minus 4 divided by x minus 2. Hopefully you're comfortable graphing the equation y equals x plus 2, and you'll notice that I labeled them f of x and g of x, and that's just to make sure you know they're 2 different functions. But hopefully you're comfortable with this guy. Slope-intercept form starts at 2, up 1, over 1, nothing too bad. We'll be as accurate as we can. And then we'll get this line filled in here, some arrows to show it goes forever. Nice continuous diagonal line. Lovely. Now, the second problem might have stumped you a little bit more. This is known as a rational equation. Rational, right? The root of that being ratio. A rational equation is a ratio, generally of polynomials to each other. So we have a parabola being divided by a line. And the question is, what does the graph look like? So you might want to go ahead and graph this on your calculator. That's totally fine. I have 2 calculators that I'm going to be demonstrating with here. These are the 2 most common ones that I see my students use. One is the TI-84. If you have a TI-83, it's okay. I would really recommend you upgrade to a TI-84. They're pretty cheap. You can get newer, nicer ones in color too. And then the other one I have is the TI-Inspire CAS, or the TI-Inspire CX. It doesn't have to be the CAS, not a big deal there. And I'll try to bounce back and forth between both of these, so you might find yourself skipping forward in the video if you already know how to do something, or if I'm talking about a calculator you're not using. If you have any calculator questions about a different type of graphing calculator, let me know. I'd be happy to respond to those in the comments. One thing that is not allowed on the AP exam is a non-graphing calculator. So if you have a scientific calculator that you really like, unfortunately you're going to have to put that off to the side. It might gather a little bit of dust, and you need to be comfortable doing any and all calculations on your graphing calculators. So go ahead and flip those on. On your 84, you can do second quit to get back to your main calculation screen, but we want a graph, so we'd go into that y equals. If there's already something in there, we'd want to clear that out. And then the one thing we don't want to do, and I'm going to erase this in just a second, is do x squared minus 4 divided by x minus 2. That's actually not the right equation. Your calculator interprets everything in terms of PEMDAS. So if you think about that equation, what your calculator would actually do is your calculator would try and graph y equals x squared minus 4 divided by x minus 2. And that's because on our calculator over here, you only have the 4 and the x dividing. You'd want to divide the whole thing. And one way you could do that is you could put parentheses around the x squared minus 4, and then parentheses around the x minus 2. But these 84s are all updated at this point, and if yours doesn't do this, just let me know or look online. There's a quick, easy way to update or fix it. But if you hit the alpha key, these F1, F2, F3, F4, F5 are all in green. They're all shortcuts to do different things, and alpha F1 does a lot. In particular, it will give you a fraction, which is very useful. And now we can just type in our equation, x squared minus 4 divided by x minus 2. Before you graph, if it's your first time using the calculator for the day, I would almost always suggest that you do a zoom standard, zoom 6. However, if you don't, I'm just going to graph right away. I think this is probably already my standard window. That standard window fixes a lot of issues. If someone else has used your calculator, if you used it and you changed the window settings, if something isn't graphing, try zoom standard and you'll find it'll fix many of those issues. Zoom standard just makes your window go 10 by 10, 10 up, 10 across, and it makes it not too far zoomed in, not too far zoomed out. Okay. On the CAS calculator, we really want to live in the calculate and graph screens. I see a lot of my students go down to this graph down here. It's like, oh, we're doing a graph. That's something that we actually don't want to play around with. It's going to take up all the memory on your calculator really quickly. There are uses for these apps down below, but we don't want those. We just want to switch between calculate and graph. So here's calculate. You're like, oh, do I have to hit the home button and go back to graph? Well, you can, but the quickest way is actually to hit this calculator button on the upper left. It switches back and forth between the calculate and the graph screens. Now, same idea, you might not have this f1 of x equals right away. I'm going to hit escape to get out of it. You might even have a graph on here. To clear out your graph, just hit delete 3 times, 1, 2, 3, and delete everything on the screen. Now, to get back to the y equals or the f1 of x equals, the better way to do it is to go to menu. Pretty much everything on the Inspire lives in the menu button, which actually makes it pretty easy to navigate. Just press menu for whatever you're looking for. We are trying to enter a graph. So we're going to go over the type of graph we want to enter is a function. Right? Sometimes your calculator will get switched to these other ones. A really common one is this REL, this relation, and people will be like, oh no, my calculator's broken, there's a relation up there, I don't like it. Well, that's fine. My calculator is having some issues there, but that's fine. Second try. So the easy way to fix it is you go menu, 3, 1, and now you're back to your function menu. Easy enough. We can also make a fraction or a ratio pretty easily. Control and then divided by, and now we can do the rest. X is down at the bottom. We have our squared minus 4 divided by x minus 2. There we go. Now, we have these two, and it seems like actually this graph is identical to the first one, right? This graph starts at 2 and it goes up 1 over 1, up 1 over 1. Okay. I've actually prepared this on Desmos as well. I think it's just a little bit more clear and neat to see this through. So when you're looking at this, right, you're like, oh, this is exactly the same, right? Here's x plus 2, and here's the other one. They take over each other perfectly. And as I glide across each of these, right, you can see what all the y values are. It looks very nice and neat. And as I glide across these, you see the exact same thing except right about here. Oh, wait, something weird happened. At 2, this guy is undefined. There's actually a hole in our graph. And you'll notice that Desmos and the 84 and the Inspire all don't show the hole on that graph. And that's because your calculators don't actually do a continuous line. What they actually do is they put a whole bunch of points on here, and then they draw a line through those points. Now, how many points? There could be thousands or tens of thousands of points. but the odds that they put the point that's at 2 comma 4, which contains the hole, is pretty slim. So they just put a bunch of points and say, let's draw a line through those, right? It's pretty good. Maybe we missed a hole, but a hole doesn't really change the picture of the graph. So long story short, you can't trust your calculator to tell you the whole picture. So let's jump back to this and think about what the heck we were doing here. We had g of x, we had this guy, and we said that there was a hole at, it looked like 2 comma 4. I'll put that on there just so we'll change colors really quickly, at 2 comma 4. Now, why is there a hole there? Well, you might remember back in Algebra 2 that you can factor this top. It's a difference of squares, isn't it? And the denominator is just x minus 2. These cancel, and it says, oh, the equation g of x actually simplifies to x plus 2. So you might ask yourself the question, well, isn't that the same as this x plus 2? Shouldn't it be this nice continuous function where it doesn't have a hole here? Well, no, g of x is this original function. Simplifying can help you graph it, but to see the whole picture, you need the original function. So we simplified down to here, but we need to keep in mind that there was a hole at x equals 2, because 2, when that's an x value, turns the denominator into 0. And when you divide by 0, bad things happen. The world explodes. You can't divide by 0. So I'm going to go ahead and put all these points in here. We can see, though, that these graphs pretty much look the same, except for that one point at that hole. Now, sometimes it confuses students to see a hole in a graph here, and they think, what does that hole really mean? Well, usually, or maybe it's better to understand that there isn't actually a circle there. We mathematicians put a circle there to make it obvious that there's a hole, but what it really means is that this one particular x value, this is at x equals 2, there is a gap in our graph. These two pieces are unconnected. So if you're walking along this graph, moving along, right at this point you'd have to jump over the hole and then continue on. Or if you were drawing it, you'd have to pick up your pencil. Now again, we put this open circle here to make it very apparent that there is that gap, but there's no actual circle on our graph. It's the absence of a point. All right, with all that talking, let's get something done. Let's have you go ahead and compare the values all the way down here. F of 1, g of 1, f of 3, g of 3, and so on and so forth. And some of these go pretty quickly, right? F of 1, you're like, oh, we have the graph. F of 1 is 3. Now, if you didn't have the graph, you of course could have taken the 1 and put it in for the x and said 1 plus 2 is 3. Same idea there, nothing too bad. But we have a graph, so we might as well use it, right? F of 3, we go to 3, we jump up, we see that that's 5. Easy enough. We can do the same thing with g of x as well, right? G of 1 is 3 as well, and g of 3 is also 5. So I can just say that also equals g of 3. Very nice. But then we get into these decimals, and you might be able to find the answers to the decimals, no problem. Don't forget, though, that you do have a calculator, and your calculator has a very, very useful trick that not a lot of students know about. So let's take a quick peek at that, right? We have currently graphed a function that is known as x squared minus 4 over x minus 2. And the 84 has named that function y sub 1. This is a little subscript, one of those tiny ones next to the y. The Inspire has named your function f1 of x. They have this of x in there. And with names come power. We can use those names to perform operations, right? So if I'm jumping back here and I wanted to find f of 1.5, that's pretty darn easy because the equation for f is pretty easy. It's just x plus 2. Say 1.5 plus 2, oh, that's certainly 3.5. But then you get to g of 1.5, and maybe you hesitate and you say, well, I don't know. Should I use the simplified equation? Should I use the original? You should probably use the original. Not a bad thing. And you're like, I don't want to plug 1.5 into that equation, and I don't blame you. So we jump back to our calculator. We go back to the calculation screen. I'm going to hit this button up here, calculation screen, and we call the name of the function. The function that I have graphed was f1 of x. Okay, you'll notice when I typed f1, it actually turned bold, and I can show you that really quickly. F is not bold, but as soon as I type the 1, it is bold. Right? If I type 2, it's not bold because I have nothing in f2 of x. So f1 of x. Except I don't want to find f1 of x. If I hit enter, they're just going to say, oh, that's weird. It's an equation. Why do you care about that? We want to find f1 evaluated at 1.5. Right? So when we find f1 of 1.5, your calculator will take 1.5, it'll go back to the equation called f1, and it'll substitute 1.5 in. So I'd like you quickly to practice that for the rest of these. Even if you think, oh, I could do these in my head, I agree. But for the g function, which is confusingly called, and I'll title this up here, f1 of x on my Inspire, I'd like you to do that for the rest of these because it becomes very useful to substitute gross values into tough equations as we move through calculus. It's a very common use of our calculator. So we saw that this was 3.5 as well. You'll also notice that I only told you about the Inspire. The 84 does this as well, and it's actually in your alpha menu. That's the easiest way to do. Now again, our equation is called y sub 1, so I'm going to go to alpha and then f4 this time. If you're not sure which one, just try the different ones, and you'll see them all pop up here, right? There's 4 different shortcuts. Okay, we're going to do f4, and notice that they have 10 different function names. The only one we care about is y1. So we're going to do y sub 1 of not x, but of 1.5. And that's going to give us 3.5. All right, not a surprise because we already found 3.5. So why don't you guys go ahead and determine the rest of these values, and then we'll come back together and chat about them in maybe a minute or two. Just unpause me whenever you're ready. So ready, set, go. All right, and we're back. Hopefully you found the same values that I did. I filled them in. I don't think I need to talk you through them. One thing you should notice, though, is that I was very particular about my notation. I didn't just write 4.5 and 4.5. I showed what I was trying to find and the answer that went with it. And that's going to be a very common theme throughout this year. Exactly 50% of your score on the AP exam comes from free response questions. And the graders are very picky about your notation. They always want to see a setup and an answer. Now you can show more work. For example, on this problem over here, I showed to find f of 1.5, I substituted in 1.5 and I got the answer. But absolute minimum, you need to show a setup. What are you trying to find? We're trying to find the function f evaluated at 1.5. And an answer. They are also very particular at how you write your function notation. You might have said something like f of x equals 4.5, but that's not right. In fact, that's a false statement, and you are penalized for giving false statements on the AP exam. F of x is not equal to 4.5. F of x is an equation with x. F of x is equal to x plus 2. F of 2.5 is equal to 4.5, but writing something as innocent as this will actually lose you a point on your free response question. So make sure you are careful and true to that notation. Now, I paused with f of 2 and g of 2. F of 2 wasn't bad. You end up doing 2 plus 2 and you get 4. But g of 2, and just taking you through the whole process, 2 squared minus 4 over 2 minus 2 will give you 0 over 0. And when you try that on your calculator, you'll end up getting some sort of error. In fact, the common way to say that this point is an error is we actually say does not exist, or do not exist, you'll hear sometimes. And the way that pretty much everybody abbreviates that is DNE. You'll even see that as possible multiple choice answers on the test. So when we say g of 2 over here, I would just say g of 2 DNE. I don't even need an equals here because g of 2, we only use an equals if we equal a value. This just says g of 2 does not exist. The value of the function g when 2 is substituted in isn't there. And that's why, if we look up at this graph, g of 2, if you look all the way up and down, has no actual point on the equation. I'll take out that circle as well. Now, if you didn't have this graph that we did earlier, could you estimate at least approximately where g of 2 should be to close the gap? I know visually you're like, well, clearly it should be at 4, and then it would be, a nice smooth, we call it a continuous function. But what if you didn't have this? Is there something in the calculations we performed over here that would tell you that if g of 2 was 4, that it would close the gap? Well, you might notice that just slightly smaller than g of 2 was g of 1.9999999, right? $1.99 and even closer to $2 gave us 3.99999, almost 4. And just slightly past 2, g of 2.001 gave us 4.00001. So if we were following the patterns, we went from 3.99999 to 4.0001. Wouldn't it make sense that g of 2 is somewhere in between those, probably equal to 4? Right? Now, g of 2 doesn't equal 4. G of 2 does not exist. But it is important to realize there are differences in the graphs. They're very similar, but slight differences. Okay? Now, what we've done here is really look at the idea of a limit without calling it as such. So let's go ahead and start into some definitions. Limits, there's that word, give us a way to analyze what happens as an equation gets infinitely close to a point. So if we look again at the two equations from the opener, and you're probably sick of them by now, but that's all right, f of x and g of x, as we substituted in x values closer and closer to x equals 2, we notice that f of x and g of x both approach the same number, right? As we used numbers really close to 2, these were the same. And as we used numbers on the other side, but really close to 2, these were the same. And it looked like 3.999, 4.0001, that they were both approaching or getting close to what number? What is 3.999 or 4.0001 close to? They were both approaching the number 4. However, exactly at 2, f of x did indeed equal 4, while g of x did not exist. I'm going to scratch out that equal sign. So here's actually how we notate those two concepts. Here are f of x and g of x redefined. F of 2 equals 4. This means at x equals 2, right? Specifically at an x of 2, the value of the function defined as f is 4. And at x equals 2, the g function does not exist. However, what if we wanted to tell someone what happened really, really close to 2? We knew it didn't exist at 2, but what about close to 2? Well, the way we do that is with our limit notation. And a limit expression has 3 parts to it. Let's notate how to pronounce them. The first part is the L-I-M, and that is just pronounced limit. I usually do my L as a cursive so you don't think it's a 1 as a heads up. So we would read this as the limit. The limit. Okay? Then we have the x values. We read this as x approaches 2. So up here we would say the limit as x approaches 2, and then we have the last part. This is the function name. However, there's a couple ways to interpret this, so I'm going to give you those different ways, right? So we have f of x. So as x approaches 2, we would say either f of x, right? F of x, easy enough. Or we could say the outputs approach. It's supposed to say approach, but we get the idea. And I'll read it both ways and then explain what I mean. So the way that's more common is you would see the limit as x approaches 2 of the function called f of x equals 4. Or even shorter, the limit as x approaches 2 of f of x equals 4. However, I like to read this as the limit as the x's approach 2 is the outputs approach 4. Right? What they're telling you is as the x's, as you plug in x's closer and closer to 2, the y values, right, these are the outputs, get closer and closer to 4. However, again, most people would just say the limit as x approaches 2 of f of x equals 4. You are required to write all 3 of these pieces. Leaving off a piece is incomplete notation and you will lose a point. We'll talk notation a lot this year. So here are some common mistakes. Why don't you guys take a look at these 4 and decide, first by saying them out loud and second by writing down what the mistakes are. So try talking it out first, what is missing from the explanations above, and then correct it. All right, ready, set, go. And you're back. All right, let's get to it. This says the limit as x approaches 2 equals 1. My question as a grader, especially if you look at this page, is we talked about two different functions here. What if they have two different values of a limit? Which function are you talking about? You're not clear, right? This needs to be the limit as x approaches 2, and pick a function, it doesn't matter here, I'll just use f of x equals 1. They forgot the f of x. It is required. Our second one is the limit of f of x is 1. Well, where is the limit of f of x equal to 1? We need a specific x value, right? We could have looked at this graph up here and we could have said the limit as x approaches 0, this is 0, right? So as we get closer and closer to 0, the y values are getting closer and closer to 2, right? You can do a limit anywhere. It doesn't need to be a discontinuity, this gap in the graph. And so we need to specify which x values we're talking about. So the limit as x approaches what? Well, pick any number you want. I don't know, we can say 5 if you'd like. The limit as x approaches 5 of f of x is 1, but you have to have the x approaches. Okay? Our third one isn't so much a mistake, but making sure you can notate what's happening. The function called f has the property that as the x's get closer and closer to 4, the values of f of x get closer and closer to 7. Let's go ahead and write this using limit notation. Well, the easy part with the limit notation is the LIM piece. And then the x's have to approach something. And while they tell us the x's get closer and closer to 4, for what function? F of x. And they're telling us that as the x's get closer to 4, the y's get closer to 7. Last but not least, the answer to this problem is the limit as x approaches -3 of f of x is 5. Jake writes this as this guy right here. Why do we not receive full points? Well, this is just like number 1, isn't it? We forgot the name of the function f of x equals 5. Okay, we have the idea on notation. We might still be a little shaky about what a limit is, but we need to examine the core concept of a limit before we start figuring out how to find the values of them. The main core fundamental concept of limits that you need to keep straight is, and you can repeat this out loud if you'd like, limits do not talk about what happens at the point, only infinitely close, right? So up above, we saw limits that talked about close to the point, and then we saw this function notation which talks about what happens at a point. So if you see the limit as x approaches, I'm just going to say a, of f of x equals some value L. This is saying as your x's get closer to whatever this number is, your y's are getting closer to that number. Nowhere in there do we say when the x's equal this number, the y's equal that, right? This is a limit. What happens at the point, that is f of a equals L. This is a specific point. This talks about what happens at a point. This limit talks about what happens close to a point. Now, if that's still unclear, that's okay. We have many days to examine the concept of a limit. So let's discuss what our progress is going to look like, and not only for this unit, but for every unit of study for calculus. In math, we try to approach topics in 4 ways. The first way is graphically. Think graphs, just like we did on the first page of this packet. The second way is numerically, and often this is known as tabularly. Tabularly, which is a mouthful to say, means data presented in tables. Think those XY tables, input-output tables. There's actually classes called numerical methods where you collect data in tables and try to analyze it, oftentimes using calculus. The third way is algebraically. Think equations, doing algebra, doing things to both sides of an equation. And last but not least, in a written manner, which you should think word problems. All 4 of these are tested on the AP exam and somewhat in a equal manner. You should expect about 1/4 of the questions to be about graphs, 1/4 tables, and so on and so forth. This will give us a really well-rounded view of any topic. Today, we're just going to explore limits with the tabular approach, which means making tables for an equation. However, making tables for multiple equations gets a little tedious, so we'll take the easy way out and use a calculator. So one word of warning, you do need to make sure your calculator is in radians, and that's because calculus is rad. The only time I think at this point in your career that you would change your calculus to degree mode is if you're taking physics. And so if you are taking physics, you're going to have to remember to switch back and forth. Otherwise, your calculator will stay in radians for probably this entire year. How do you put your calculator in radians or check it? Well, most of your calculators default to radians. Mine is up here. If your calculator is up to date, and see your teacher if it's not, you should actually be able to lightly run your finger over the trackpad until you see this mouse moving around on the screen, move it up to radians, and click it. If you click it, it will change to degrees. If you click it again, it'll change back to radians. But mine's in radians, no reason to change it. On the 84, your quick check should just be in mode, and then right down here to radians. If degrees is highlighted, make sure you go left, hit enter on radians, and then back out. A very easy way to figure this out, and a nice review for you in terms of trigonometry, everyone's favorite, is you can find the cosine of pi. The cosine of pi, if you are in radians, will be a nice number. Degrees, it will not. Do you remember what the cosine of pi is? Well, hopefully you said it's -1 because it is. And you would do the same thing on your Inspire, right? Your trig functions hide in here, and we've got our cosine, which my calculator really does not like me using the pen as an input, but that's okay. And then the pi button, by the way, is hiding down here under the pi symbol, and we've got cosine of pi. Okay. There we go. So we are in radians. We are ready to get started. Let's make some tables. All right, we come to our first example. We're going to look at the equation defined as y equals f of x below. By the way, you're going to see this notation very often. This means the outputs are called y, the inputs are called x, and f means things are happening to x. In our equation down below, the things that are happening to x are that x is being signed. That's not a real thing. We are taking the sign of x, and then we are dividing by another x. So this sign and this division and this x are the things that f is doing to x. So y is the output, f is the stuff happening, and x is the input. Either way, we're going to go ahead and evaluate f of 0 without a calculator. So f of x equals sine of x over x. F of 0, we know, just means to replace x with 0. Sine of 0, hopefully we remember how to calculate that, right? We know that's a rotation of 0 radians. This is the point over 1 up 0, and sine is always the y. So we end up with 0 over 0, which means f of 0 does not exist. Okay. Well, we're going to go ahead then and use a table to figure out what happens. My screen jumps around every now and then. What happens around 0. In fact, we're going to try to answer the question, what is the limit as your x's get closer to 0? Because we saw f of 0 didn't exist, but what happens close to that point? Do those points also not exist? Well, what we're going to do is to make a table, we're going to have our inputs and our outputs, x and y. And I usually do between 5 and 7 individual things, individual little columns here. I'm going to do 7 this time. So here's 1, 2, 3, 4, 5, 6, and 7. We always want to center the x value that we're interested in the middle of our table. So we are getting close to 0. 1, 2, 3, 4. Here is 0, right in the middle, right? We know that the output when x is 0 does not exist. What I'm curious about, though, is what happens close to 0. And so to determine this, we need to figure out what are some numbers close to 0, numbers that are a little bit more negative over here, a little bit more positive over here. One number we know is pretty close to 0 would be like the number 1. And on the other side, its counterpart is, of course, -1. So let's go ahead and see what happens if we find f of 1 and f of -1. Now, I mentioned that we can do this with our tables here, so we're going to go ahead and get that rocking and rolling. I'm going to clear everything out of my graphing screen, delete 1, 2, 3, and I'm going to go ahead and get my 84 rocking and rolling. We'll clear this guy out. We need a fraction, good practice for you. So we have sine of x, close your parentheses, over x. I'm going to graph this. And then we'll do the same thing here. So, by the way, a shortcut to get up to the entry edit screen for the Inspires, you can just hit Tab. although most of you will end up doing that, please, please, please don't forget that you can also get there from menu 3-1. And when in doubt, if tab is doing weird stuff, menu 3-1 is going to be your savior. So I'll make this guy right here. Yes, 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 thank you. I have fat fingers, I understand that. Trig and sine. That's really, really frustrating. I wonder why it's doing that. That's okay. Sine of x over x, and we're going to graph that too. Now, graphically, we're kind of doing a weird thing here because graphically, you might be able to see what happens as x approaches 0, right? You're like, well, the x's are less than 0 here, greater than 0 here, and right at 0. It looks like the graph is hovering right around 1. Right? Same thing over here. But we're going to pretend that we don't have a graph. And there's more about this later on. It's just easier to start with a graph. But we're going to go ahead and pull up our table. So to do that on the 84, second table. To do that on the Inspire, we're going to go to Menu, Table, Split Screen Table. Now, you might notice that on the Inspire, and we can go up and down here, right? I have -1 and 1 and 2, and that's very nice. But on my 84, nothing popped up. That's because my table is set up by some other user, spoilers, it was me, but who didn't set it back to regular settings. To reset the table, you go to Second, Table Settings. Okay, and I want it to be auto for both of these, independent and dependent. We'll talk about what those are shortly. And I want my change in my table, I want it to go up by 1s, and we'll have it start at 0. So it starts at 0, goes up and down by 1s, auto for both of those. Now I'm going to go back to second table, and we'll see everything here. Right, they look just about the same. You'll notice if you roll over to this, you'll get the expanded decimal. Same thing down here, but you might just see a few numbers right here. We also get an error at 0. So it looks like 0.841 for each of these. So 0.841 and 0.841. Okay, not too bad, but it doesn't really answer the question because as we get infinitely close to 0 is what a limit tells us. How do we get infinitely close? Well, it's got to be closer than -1 and +1. What's closer to 0? Well, if we think about money, what's the closest we can get to 0 with money? You might say, oh, 1 cent. 1 cent is 0.01. And that is pretty close to 0. -0.01, +0.01, very close to 0. So what are the outputs there? Well, you might notice that back on our calculators here, they don't get that close to 0. And so I'm actually going to give you two options here. Option 1 is you can go to your table settings and you can have it go up by smaller and smaller decimals. You can say, I want it to go up by like 0.01s. Right? But then if you do that and you get to your table, you realize if you wanted to get to -0.01, you have to go down really far. You could always start your table at a different number, but there's actually a better way to do this. And the better way to do this is to change, and this is what I had actually done earlier, change your independent variable. Instead of the table filling in the independent variables, that's what you control. Those are the x values. Instead of them automatically filling them in, let's have them ask you what independent values you would like to substitute in. And then it will automatically calculate the outputs. So when I do this, when I go back to the table, it'll be blank. I'll do the same thing on the Inspire. Menu, table. You can remove the table here if you need, but we're going to edit the table settings, which is 5. And we're going to do the same thing. We're going to change the independent to ask and hit OK. We need to go over to the x's here, and now take a look. If I wanted to find an x of 0.01, we'd type it in, hit enter, and it says, oh, there's the y. Same thing on the Inspire. Let's try the -0.01. Oh, there's the y. 0.999, so 4 9s and an 8. So 0.1, 2, 3, 4, and an 8. 0.1, 2, 3, 4, and an 8. Now, what if that's not close enough? Because we said infinitely close to 0. And we can get closer than 0.01, can't we? We could go to like 0.0001, or same thing on the negative side. You could put as many zeros as you wanted. But my guess is if we're that close to 0, we'll have a really good idea of what the y values are close to on both sides. So let's jump back. Let's do each of those. So we have, I think I did 4 zeros, right? I'll double check though. I just did 3 zeros. Okay, that's fine. And I have an extra decimal here. 1, 2, 3, and that one. and then I will do the same thing over here, but with a negative. 1, 2, 3, and this one. Okay, and they told me it's actually 1. Well, actually, there's a few weird things that are going on here. If I go over, it's not actually 1. It's 0.999999998, which the calculator rounds to 1. It will automatically round after a while. Same thing on the 84. You'll also notice that instead of writing it as 0.0001, if I highlight this on the Inspire, it says 1 decimal e negative 4. We do need to remember our scientific notation. If you see 1 e negative 4, what that really means is 1 times 10 to the negative fourth. And we know if we multiply by 10 to a power, it either moves the decimal to the right if it's a positive exponent, or to the left if it's a negative. So this is the same thing as 1, 2, 3, 4, which is that 0.0001. Your calculator will use this pretty often with large or small decimals. So just remember that depending on if it's positive or negative, it means either a very small number, or if you had something like 1e 10 to the 20th, a huge number, right? That would be 20 decimals to the right. Okay, and it does that to save space. But either way, we got 0.999999998, something like that, or, approximately 1. All right, now I'm pretty confident to the answer to this question, which was what was the limit as x approaches 0 of this function? Well, as my x's get closer and closer to 0, what do the y values get closer and closer to? Originally, it was like only 0.84, then 0.99999, and then really on either side, we were really, really close to 1. So we would say that the limit to this is 1. Right? If you were to get infinitely close to 0, if you were to put an infinite number of zeros here, you would essentially be at 1. Infinitely close, but at 1. And that's why on our graph here, and I'm going to get rid of the table just by doing Control T, it's a nice shortcut. That's why on our graph here, we are pretty much sitting at 1. Technically, there's a hole there. You can't see it on the calculator, promise it's there, but the graph is pretty much at 1. Same thing on this guy. All right, you get the idea at this point. So why don't you go ahead and determine this next value, where we have g and my g of x function, even though it's not written here, which is fine. Our g of x function is going to be defined as the cosine of x minus 1 divided by x. Okay? We can start by finding g of 0 together. Don't write too big because you'll need to make a table like we did before. But when we go through and find g of 0, we know that that's cosine of 0 minus 1 all divided by 0. Cosine of 0 we know is 1. Right? We can see that from our graph up above. The cosine is the x minus 1 over 0, which is 0 over 0, which means that g of 0 does not exist. All right, so then what is the limit as we approach 0? Well, again, I don't know what the graph looks like, and so we're going to use the table feature of our calculator, something very, very similar to what you did up above. I don't think you'll need me to walk you through this one. 3, 4, 5, 6, 7. So why don't you guys go ahead and make your own table this time and plug in your own x values and decide what is that limit going to be based on the table in your calculator. Even if you think you don't need the table, try a few small values. The more you use your calculator, the better. Practice improves performance. And then once you're done, unpause and we'll come back together and we'll discuss from there. Ready, set, go. All right, you're back. Hopefully you found a nice easy graph for this, right? It's nothing too terrible. I'll delete this. Nothing too bad here. Okay, there we go, second try. And I'll quickly graph it. So we had this guy. All right, it's going to have those issues again, isn't it? Oh well. Second try. And we, of course, have the cosine. Oh, it's nice to me that time. Cosine of x, get outside of those parentheses, minus 1 over x. And we're going to go ahead and address a question that's hopefully been on your mind. And the question is, well, here's the graph. Why would I even need to make a table? Graphically, I'm pretty confident that the graph on both sides gets closer and closer to 0. And in fact, the limit of this is 0. You'll find that these end up being negative 0.000001 and 0.000001, which is really close to 0, ends up being 0. So again, the question though is, if I had a graph, why do I need a table? And that is an absolutely valid question. The reason is because we are practicing the skill of reading a table. Because, shockingly, in the real world, and math does actually exist in the real world, a table isn't just used to record values from an equation like we did on the last two. It's actually very common to take data observations just out in the real world, real life, and record those answers in a table. And as we're going to see later on in this course, limits will unlock a super powerful mathematical tool that's used to analyze data, the ability to determine how fast the data is changing. How does this work and what does that actually mean? You'd have to stick around for a few more weeks. But imagine for now that we don't actually know an equation, right? Instead, we're just sitting out there in nature. Maybe we're recording the number of times birds chirps as the hours move on, or the amount of water in a river every day, something like that. And we're going to assume that our data has a predictable pattern. And maybe we could find an equation, but that's not always the case, and it's also not the point of today. The question is, if we have a table and we don't have an equation, we don't have a graph, could we still find the value of a limit? And so to finish off for today, we are just going to be given a few tables, and we're going to see if we can find each of those values. All right, so looking at our third one, the function f has selected values given in the table below. Of the following, what's the best approximation for the cosine of the limit as x approaches 0 of f of x? Well, you might look up at this and say, oh, we just need an x of 0. But there is no x of 0 here. And we can't just guess at what is the value of x of 0, right? If we looked up above, if you had guessed at the value of x of 0 here and said, oh, it does not exist, you might have said the limit is does not exist. But the limit was 1. To find the limit as we approach 0 of f of x, we need to see what happens close to 0. And on the negative side, it looks like our y values are at negative 0.001. And as we get closer to 0 from the positive side, our y values are 0.001. Looks like those are pretty darn close to what y value? Well, those are pretty darn close to 0. So what I'm going to say here is that this limit as x approaches 0 of f of x actually equals 0, right? 0 is really pretty darn close to each of these y values. But we're not done yet because we want the value of the expression. We need to find the cosine of 0. Trig practice, right? The cosine of 0 is 1. So now that you get the idea, why don't you try examples 4, 5, and 6. And then once you're done, you can come back together with me and we'll see how you did. Ready, set, go. All right, you're back. Let's look at this example 4. It's a little bit trickier. Nothing too bad, but a little trickier. Right? We have this 1/2 that's multiplying by whatever the value of this limit is. This is the limit as x approaches 1. Well, as your x values get closer and closer to 1, what do the y values approach? And you might look at this and say the y values aren't approaching any nice number. And you're right, they're not really approaching an integer, but it looks to me like this one is just a little bit larger than 2.62, and this one is just a little smaller than 2.62. So I think a nice approximation, which is what they asked for, is it looks like the y values are getting closer to 2.62 here. And half of 2.62, just take half of each number, 1.31, is an answer. And so that's probably the best way to go. Right? We don't want to say it does not exist because this is the value of f of 1. f of 1 doesn't exist. The limit talks about what happens close to 1, not at 1. Here comes example 5, but I bet you have the idea now. As we look at this one, we say, okay, we're getting closer to negative 2 here. So it looks like my y values right around negative 2 are pretty close to positive 1, aren't they? So we have this ln right here. And the limit as we approach negative 2 ends up becoming positive 1. So we get the natural log of 1. But I don't see that as an answer down here. So I think, without a calculator, we need to know the natural log of 1. In fact, you need to know any log base of 1. They all are the same answer. Every answer, and you can try it on your calculator if you don't believe me, is 0. The natural log of 1 is 0, and we need to know that. That comes up all the time in calculus. It's as common as asking you what the cosine of 0 is. There are a few facts about natural log you need to know. We'll cover those later on in the course, but you should be pretty confident after Algebra 2 with natural logs, especially the natural log of 1 being 0. Okay, here comes example 6. We need the approximation for as x approaches 0. Okay, well, as we get closer and closer to 0, we kind of pause here on one side, pause here on the other side. Well, you might be tempted to say, here's 100, here's negative 100. Between those is 0, so maybe the answer is 0. But that's not how limits work. We can't just assume what's between. This is really close to 0 on one side, and if you picture a graph, we're way up here at 100. And then really close to 0 on the other side, we're way down here at negative 100. Are those 2 points near each other? Well, they'd be near each other if they're in the same spot. They are certainly not. They're actually 200 apart from each other. And so it actually turns out that our answer is neither A, B, nor C. Our answer to this is that the limit does not exist. Now let's go a little bit further here. The issue with the table when calculating the given limit is that the negative side of 0, so the negative side of 0 approached 100. However, the positive side of 0, right, that's on this side, approached negative 100. Those are 2 very different answers. So, how do we reconcile or how do we fix the issue with the table above? Well, we say that the limit does not exist. And hopefully you're thinking Mean Girls right now. You might run and re-watch that clip shortly. That's totally okay. We're going to watch it later on. But yeah, the limit does not exist, right? So if f of x approaches 2 different values as x approaches the same value, right? X was approaching 0 up here, then we say that the limit does not exist. Notice that I didn't use an equals sign here because we reserve equal signs for actual values. So the limit does not exist. All right, that's actually all we needed to learn for today. It's not a terrible lesson. It's a pretty slow-moving one because we want to cement the idea of A, what a limit is, and B, how tables can help us. We still have a lot more to explore. We need to explore limits graphically, we need to explore them algebraically, and in terms of word problems. However, studies show that starting around 6th grade or so, students need to be given time independently, and that doesn't mean at home, I don't call it homework, just away from peers and a teacher, could be in the hall, in your car, in the library, wherever, to make sure that they practice the content that they learned, not only for the day, but through the entire year. So think like practicing your musical instrument outside a band, right? Or playing a video game multiple times until you master a section. You usually don't get a musical piece perfect the first time. Same thing, you're not a master at a video game just having done it once. You need to practice over and over to improve your performance. You might not be perfect, but we want improved performance. So tonight you're going to have your first independent practice, and next class you'll have your first real knowledge check, right? We're just checking your knowledge. Think of it as a quiz. All of our independent practice problems are given digitally, so you'll need to be able to access Microsoft Teams. I do also have all my solutions on there as well. Your independent practice, by the way, is always broken into 2 sections. The first section, no more than 6 or so problems, is always a review of what we learned in class today. So the first few questions of your independent practice will be all about correct notation of limits and how to find limits using tables. Weren't those our daily objectives too, right? We needed to be able to interpret and estimate limits from a table and use correct notation. But then the second half of your independent practice, the last 3 or 4 problems, will always be review. And you might say, well, what can we review? We've only had 1 day of class. Yeah, but you've also had like 11 years of math before this. Maybe the review will be on natural logs, trig functions, rationals, geometry, right? The only way that you stay fresh with all of these ideas is if you continuously practice them. I don't care that you were good at running 4 years ago. I want to make sure that you're still good at running now. Obvious analogy for math. So I will also tell you that there are 3 important habits of successful students. And my students that do all three of these continuously throughout the year all pass the AP exam, all of them. And here are the three. The first is they do all their independent practice on time. It's assigned tonight, it's due next class. Second, they do all the independent practice with fidelity. And man, oh man, do my students struggle with this. With fidelity, with faithfulness, right? Do it on their own without having someone else doing it. And the important one, without just opening my solutions and copying the problems down. That's an absolute waste of your time. There's a reason your independent practice doesn't affect your overall grade in your class. It does affect your citizenship, right? It's because we want you to do it. Now, let's say that you don't do your first independent practice on time. You're a day late. That's okay. I would rather you be a day late and actually do it on your own with fidelity than 10 minutes before class. You go, oh no, I forgot Mr. Grant's homework. He's going to yell at me. I need to just copy his solutions. Don't do it. It's a waste of your time. In fact, I would rather you don't do the independent practice than turn it in with copied solutions. I don't want you to waste your time. And then last but not least, the very important one, you need to ask for help on all the independent practice problems consistently. If you did it, you looked at the solutions and you didn't get the problem right, you didn't understand it, your friends couldn't help, then you need to be coming into class consistently. I would expect that for each AP class, each one, you have a minimum of an hour and a half of free time to ask questions every week for every class. So those of you taking 6 AP classes, you guys are crazy. I respect you. It's a lot of extra time if you want to do it right. Email me, set up appointments before school, after school, lunch, tutoring times, anything like that so I can help you. But I guarantee if you do these three, you'll be just fine. Good luck this year. Thanks for tuning in to this first lesson. Our other lessons flow a little bit quicker since we had a lot of background info here, and I'm so excited to lead you into your success for AP Calculus.